Hello, Royals. This is for lesson 5.7 on the natural number. I am hoping to just illustrate some of the properties of Euler's number. So let's get a general exponential function up on the screen. I'm going to add a slider. So there's, I don't know, there's like y equals 2 to the exponent x, a growth curve. We don't consider 1 to be an exponential curve. There's my decay curves. Oops. Slider's a little wonky. Desmos does a pretty good job, actually, of just displaying the derivative of a function as well. I'll define g of x to be f prime of x. And there it is. So all the way back in day, I think it might have been day 2.1, we were just graphing derivatives of curves. We had a curve and we drew its derivative. So here's an exponential curve, let's say y equals 2 to the exponent x. And the rates of change are all positive. Notice the rates of change are also exponential. So as x grows, my rate of change grows. As x falls, my rate of change approaches 0 from above. And that sounds an awful lot like the end behaviors of the function values as well. What would have been difficult to notice is that when my curve is at a height of 1, my rate of change is lower than 1. When my curve is at a height of 4, my rate of change is lower than 4. If we did this through experimentation, and this is what you did a little bit of trial and error in your on the lesson. If we put in a base of 3, I can see the exact same properties. My rates of change are still exponential. And then it turns out, though, that when my function has a height of 1, the rate of change is a little bit higher than 1. When my function has a height of 3, my rate of change is a little bit higher than 3. Right. These are nice reference points here for exponential curves with bases of 2. The rates of change are lower. There's my red curve is the derivative curve. Let's try projector mode. Oh, yeah. When my base is bigger than 3, my rates of change are higher. My derivative curve is higher than the original curve. So here's what we did in class is we sort of experimented, in the printed lesson, and found that there was some special number, some sort of base, somewhere between 2.71 and 2.72, where you have a curve whose derivative is coincident with the original. Okay. Now let me try changing what it is that I'm presenting here, what I'm sharing with you. I haven't done this before, so let's see how this works. Present now, a window. There we go. Right, I want to talk a little bit about the history of this number and why Euler was credited for it. It actually comes from the idea of compound interest. And normally I would do these calculations with you in class, but we'll do what we can now. So I want you to quickly, let's review the compound interest formula. It's not a formula we need to use in this course, but we had our principal, our rate, we had to divide by the frequency, how often we were compounding. This was the number of years multiplied by how many times per year we were compounding. And we saw that compound interest caused exponential growth here. So I want you to imagine you invest $1, not a big principal, but it makes multiplying a lot easier. If you want to invest $100, your amount is just going to be 100 times my amount. I want you to imagine that you found an interest rate of 100%. The argument here, though, is that I know that seems ridiculous, but what we're going to discover is that there is a limit to how quickly you can grow. It doesn't matter how large your interest rate is. There's some sort of upper limit to how quickly your finances will compound. So an ideal situation, 100% interest per annum for 1 year. And then what we're going to do, if we keep all of these values fixed, then the only way that we could interest our amount is by increasing our compounding frequency. So if I only calculate interest once per year, I'm compounding annually, then my compound interest formula will tell me what I hope is going to be obvious to you, that I get a 100% return. So I end up with $2. If I compound monthly, then I'm only receiving 1/12 of 100% per compounding period, but I compound 12 times, and I punch it into my calculator, and I get this number 2.6130. So I get about $2.61, or a return of um, overall, I suppose, about like 161%. If I were to find an investment that would allow me to compound daily, I would have 365 calculations, but each one of those days I would only receive 1/365th of my 100% interest, meaning that I would end up with $2.71. If I were to compound minutely, which I don't think is the adverb or adjective or whatever that you use here, but every minute there are 525,600 minutes in a year. So I would receive 525,600 compounding periods. Each one of those periods, I would only receive 525,600ths of my 100% compound interest rate. So I would end up with $2.71, 72 cents, somewhere in between $2.71 and 72 cents. Again, if I wanted to get more money, I could always invest more. I could try to find a higher interest rate, but I doubt I'm going to find a better interest rate than 100%. The other option is I could compound more frequently, and there is a limit to how much higher I can get by compounding more often. If we are to try to compound continuously, try to imagine some sort of natural situation where these are all discrete models. These finance models are discrete models. This isn't how radioactive decay works. It doesn't wait for a half-life to go by and then pop off half of its mass. It's happening continuously. We would argue, or all the time. A natural growth can usually be modeled by more of a continuous function than a discrete function. If we imagine that we are compounding interest every single instant, every fraction of a second, an infinite number of times during every second, then your compound interest output becomes the output of a limit. We want our number of compounding frequencies to grow without bound, and that means that my interest rate here is actually per compounding period is going to decrease. It's going to approach zero. This is a very interesting indeterminate form. We have an exponent growing without bounds. So you have an infinite number of multiplications of something that is becoming infinitely close to 1. It's 1.000000. It's never going to be 0, and this will grow without bound. And you have a very interesting balance there that your output will approach Euler's number, that very special base for us. And this is why it's called the natural base. Euler was a banker, so I need to brush up on my history, but I wouldn't be surprised if he discovered this number or made this number popular by experimenting with discrete situations. And then it turns out that it's super useful in continuous situations. It was mentioned on the lesson. This is one of the mathematic definitions for this constant, for this number. You won't be expected to memorize any digits of the number. I don't think anyone celebrates Euler Day on the 71st of February. It's nice to know where these numbers come from. If your understanding after this lesson is that E is a very important constant in mathematics like pi, then you're in decent shape. And then we will try out some derivatives with it and work on applications. So, look up the history of this number. There's a lot of interesting things that come up with Euler's number.